Hi, everyone. So this is just a short video that really goes along, actually, typically with our last lecture. I had just felt that that last lecture was very packed with information, starting to get a little bit long, and so I thought I would just split it up and record this one separately. And so there are no warm up questions or anything like that. We're just going to dive right into that little bit of missing material. And so this last bit of that lecture, here we go, starts to get into what we call periodic properties and being able to look at the periodic table and think about electron arrangement in order to predict and talk about certain properties of the atom. And so we have to remember that the periodic table, the way that it's set up and the way that it was sort of invented, for lack of a better term, is that elements were first arranged in order of increasing atomic number. The periodic table was actually arranged before electron configurations were even known. And so we say that properties of elements then are what we call periodic, meaning that those properties repeat themselves every few elements. And we've talked about that a little bit, and we've seen it, where it's like the alkali metals, for instance. All our alkali metals here all have very, very similar properties, and thus we give them that family name to make it easy to distinguish them. It turns out, though, that if we think about the electron configurations of these, the electron configurations of all of these elements end with S1. But again, we set up the table. I say we, Dmitry Mendeleev and Lothar Meyer really did a lot of this work. But the table was initially set up before we knew about these electron configurations. It was just arranged in such a way that elements with similar properties ended up being in the same column. We found out later that that is because they have very similar electron configurations, especially that last bit of their configuration. And so what we're going to talk about today are some other types of properties associated with atoms, such as the size of atoms and ions, and something called ionization energy and electron affinity, which relate to how easy it is to either take an electron away or add an electron in when forming ions. And so in order to look into this, we have to define what we call effective nuclear charge. The effective nuclear charge is pretty much, if we're talking about electrons that are, especially out on our outer shell, or I mean, we could be talking about any electrons, but if we're talking about electrons on the outer shell or anywhere in the atom, the effective nuclear charge essentially says how much does that electron feel the pull of the nucleus? How much is that electron being pulled in by the positively charged nucleus? And the outer electrons are shielded by the inner electrons. And that should just make sense, because electrons are negative. And so if we're thinking about the effective nuclear charge on this electron right here, so how much does this electron feel the pull of the nucleus? Well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in between this electron and the nucleus. And so those 10 electrons are going to shield this one from the nucleus. And so to calculate the effective nuclear charge, we're going to use a simple calculation. I can't remember, honestly, if your book goes into the more complicated calculation. There is a more complicated calculation as well. But we're just going to look at the simpler calculation where the effective nuclear charge is equal to Z. Remember, Z is just the atomic number minus any of the inner electrons. And so in this example for phosphorus, Z is equal to 15, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inner electrons to give us an effective nuclear charge of +5. Let's look at an easy way that you can find the number of inner electrons, because we haven't really talked about that yet. I don't think I've set this up to be able to. Sorry about this. I thought I had set up my player already, but I hadn't. What is going on? Why is it acting up? Simplest thing, quit out and then come back. So we'll do that. Okay. Once again, there's two of me. You don't need that. Here's our screen. Okay, so let's write out our electron configuration for phosphorus. Phosphorus has its 15 electrons, so we get 1s2, 2s2, 2p6, 3s2, 3p3. So there's our configuration for phosphorus. If we're calculating our effective nuclear charge, it's going to equal Z minus our inner electrons. The inner electrons are going to be all of the electrons on the outermost Bohr shell. And so when we look at the Bohr shells associated with phosphorus and where the electrons are, we have some electrons on our first Bohr shell, we have electrons on our second Bohr shell, and we have electrons on our third Bohr shell. And so the outer electrons then are any electrons on the third shell, which means that the inner electrons are really all others. And so in calculating our effective nuclear charge, Z for phosphorus is 15, and our inner electrons are anything on Bohr shell 1 and 2, so 2, 4, 10. That's a minus, there we go. 15 minus 10 equals our plus 5 for the effective nuclear charge of phosphorus. And we'll see how we use this in just a second. And so that should make sense to you then, that the effective nuclear charge will increase right to left, or sorry, increase left to right across the periodic table. And so again, if we just sort of just turn back to here, if we look, for instance, at, remind me what's after phosphorus, sulfur, with its 16 electrons, and so Z effective for sulfur equals 16 minus our inner electrons. And so for sulfur, the only thing that changes in our configurations is 3p4. So our number of inner electrons does not change. So this was for phosphorus here, now it's for sulfur. And so we get a plus 6 for the pull on a sulfur atom. And so as we move left to right, the effective nuclear charge is going to increase. The other way to think about it, so this is how we would think about it quantitatively, by actually just calculating Z effective. The other way to think about it is that as you move, for instance, from phosphorus to sulfur, phosphorus has 15 protons holding in 15 electrons. Sulfur, 16 protons holding in 16 electrons. So there's a little bit more of a pull. There are more plus minus interactions on sulfur compared to phosphorus, so you get a little bit more of a pull there. So there's a little bit more of a pull exerted by the nucleus. So Z effective increases as you move left to right. And so let's think about what this does to the size of an atom. Now things are going to be a little less intuitive for you here, because you would think, and it's natural to think so, that for instance, as you move from sodium to magnesium, you'd say to yourself, well, I'm increasing in atomic number. I'm getting one more proton. I'm getting one more electron. Magnesium's probably bigger than sodium. But that's not true. It's actually the exact opposite, because Z effective increases as we move left to right. Our effective nuclear charge increases. This means that the electrons in magnesium are held in a little bit tighter than they are with sodium. That shrinks the atom down a little bit. And so magnesium is a smaller atom than sodium. And so the size of atoms decreases as you move left to right. So if we're looking here in the third period, sodium is the largest atom in the third period. And argon is actually the smallest atom in the third period. And so the size of an atom will decrease left to right. As you move down, however, the effective nuclear charge stays the same. And so the effective nuclear charge of sodium is +1. The effective nuclear charge of potassium is +1. But let's think about what happens there. As we move from sodium to potassium, here we have a sodium atom, and we have electrons on the 1, 2, our outermost electrons out here on the third Bohr shell. With potassium, let's pretend those are all evenly spaced. Our outermost electron is out on the fourth Bohr shell. And so the size gets bigger. The size of an atom increases as you move down because we're going to further and further out Bohr shells for our electrons. And so size of atoms increases as you move down, and it decreases left to right. One way to think of this is this means that francium is actually predicted to be the largest atom in the periodic table, whereas helium would be predicted to be the smallest. And this just sort of goes over everything that we just talked about. I'm going to skip through these real quick. And like we talked about here, so the nuclear charge decreases as we move right to left. So the size would increase. But as we move down, we're getting further and further out. And this just shows us some of those relationships. This is what I was looking for. And we can really see it here. So here's the relative size of a lithium atom compared to a fluorine atom. So we're moving across period 2. And so we can really see that we get smaller and smaller and smaller. A couple anomalies in here, which you might be able to see visually, that we're not going to really worry about. We have here in the fourth period, potassium over to bromine. But we can see moving down that we definitely get a lot larger. And so to recap for atomic size, the size of atoms goes up as you move down a group because electrons are added further out from the nucleus. So there's less attraction and they're just further out. But size decreases as you move across the period because the effective nuclear charge increases. The pull on those outer electrons increases. The next trend to talk about is what we call ionization energy. Ionization energy is the amount of energy required to remove an electron from the ground state of an atom. We talk about ionization energy in terms also of it happening more than once. And so for instance, ionization energy 1, the energy needed to remove the first electron. So if we have potassium, we're going to go ahead and remove 1 electron from potassium to make it K+. That's going to require a certain amount of energy. I2 would be the second ionization energy, and that's the amount of energy needed to remove a second electron. So now we're removing an electron from a +1 ion. So here's our K+. We remove an electron to make it K2+. Now that should look funny to you, and you're right, K2+ we talk about as not really existing because K+ is the preferred ionic form of potassium. But given the right amount of energy, we could make this happen. We could force potassium to lose an additional electron. Doesn't happen as far as the normal course of events that you're going to be worried about. For instance, with coming up with chemical equations and whatnot, you're never going to have to worry about a K2+ ion. But we do talk about it here in terms of the energy that's involved in removing some of these electrons. You'll see there's a big jump in energy there. It takes a lot more to remove the second than it does the first, and we'll talk about why. And so ionization energy increases as you move left to right. So it increases because the effective nuclear charge increases. Those electrons, as you move left to right, are held tighter, so it is harder to remove them. And so the first ionization energy of magnesium is higher than the first ionization energy of sodium. It takes more energy to remove an electron from a magnesium atom than it does from a sodium atom. Similarly, ionization energy increases as you move up. And that should just make sense because something like francium, those outer electrons are way out there. They're so far away from the nucleus, it's easy to just pluck one right off. Whereas in the case of lithium, those electrons are held very, very tightly into the nucleus. And so it makes it a lot harder to remove them. And so ionization energy increases up into the right. Now let's take a look at some of the numbers involved here. And so this is all for, so we have just several elements here. And we have the first ionization energy, the second ionization energy, and then even the third ionization energy. Now, if we look at, which one are we looking at here? If we're looking at beryllium. So you'll notice that in order to remove one electron from beryllium, here we go. Beryllium's right here, one of our alkaline earth metals. So beryllium's here. It takes a little bit of energy to remove one electron from that. Now, if we think about what that looks like at that point, if we remove one electron from beryllium, then it's going to have the same type of electron configuration that lithium would have, right? It would have the same number of electrons that a lithium atom would if we take one away from here. And so then it takes a little bit more energy to remove one more electron. And so now it takes 1757 kilojoules per mole to remove an additional electron. At this point, now we've removed 2 electrons from beryllium. It now has the same electron configuration that helium has. It has what we call the noble gas configuration. Noble gas configurations are very, very, very stable. That's the sort of the ideal electron configuration for all atoms. When atoms form ions, that's what they're trying to do, is to achieve a noble gas configuration. And so it's going to take a heck of a lot more energy now to try to remove that one more electron. And so we get this huge jump in energy. We see the same thing here with lithium. With lithium, it doesn't take much energy at all to remove one electron, but it takes a lot more now to remove 2, because lithium is then at the configuration of helium. And so if we look at several just examples of that, so here we have a sodium atom, not much for first ionization energy. It doesn't take much energy at all. Because we remove 1 electron from sodium, it now has the configuration of a neon atom. It has a noble gas configuration. So it's going to start taking a lot more energy to remove electrons. Magnesium doesn't take much to remove 1 electron to get it to the same configuration as sodium. Doesn't take much at all to remove another electron. Now it's at the configuration of neon. So to remove 1 now takes a lot of energy. And we see this all through the table. Same thing happens with aluminum. So we can use this to predict what group an element is in. Element X here doesn't take much to remove the first, a little bit more for the second, a little bit more for the third, a little bit more for the fourth, but then we have a huge jump. This tells us that element X is more than likely in the carbon family. It's one of these atoms here. Because let's say, for instance, that it might be silicon. This would be ionization energy 1 to get it to a state like aluminum. Ionization energy 2 would then make it look like magnesium. Sorry. Let me back up here. It's looking behind me. I think it's thrown me off a little bit. Sorry, yep, it would be in the nitrogen group. I knew I messed that up in my head. It'd be in the nitrogen group, because removing 1 electron doesn't take much energy. Removing 2 electrons gets it to here. Removing 3 gets it to here. Removing 4. It's Monday. You'll have to forgive me. It's been a long day already. Yeah, sorry. Removing 4 gets it to here. Nope, I was wrong. Let me back up once again. Forget everything that I just said. It's been a long, long morning. Baby didn't sleep last night. So it's in the carbon group. So we remove 1, 2, 3, and then the 4th gets us to here, and then it gets very hard to remove. And so you can use this idea of the jumps, because the jump that, how do I want to put this? When you see this big jump in energy, then the row before that, or the jump before that, is going to be what column the element was in, skipping the transition metals. And so if it's relatively easy to remove 4, but very hard to remove 5, then you know the element's going to be in the 4th column. Similarly here, element Y, the first 6 are relatively easy, but the 7th now gets very hard to remove it. That tells us that we're in the 6th column here in the oxygen family. Let's say maybe it's sulfur. We're going to remove 1, 2, 3, 4, 5, 6 fairly easily. Then it gets difficult again. And so that's how we can use this ionization energy data to predict what column an element is in. And so similarly, but opposite, the electron affinity of an atom is how much energy change is there adding an electron in to a neutral atom. Typically, this is an energetically favorable process, and so usually this is an endothermic process. The trend increases. It is more energetically favorable, we'll put it that way, as you move left to right and as you move up the table. And so we can see that here, that if we're looking at our halogens, it's most energetically favorable. The most energy is released for fluorine as compared to iodine. So electron affinity increases up and to the right. Noble gases don't have any electron affinity values because they don't have an affinity for electrons. They don't want any more electrons. They are happy just the way they are. They really don't want to accept any more electrons, and so they don't have electron affinity values. And actually, we're not going to talk about that. Ionization energy versus electron affinity, just to sort of compare the two. Remember, ionization energy always measures the ease of losing an electron, always going to be endothermic. It's always going to take energy to remove an electron. Whereas electron affinity measures the ease of gaining an electron, usually exothermic, but not necessarily always. Let's look at another concept here real quick. And so if we have these different ions, we want to rank these ions in order of decreasing size. What we have to note here is that these ions are all what we would call isoelectronic. They are all going to have the same number of electrons. And so if you don't believe me, let's go ahead and just check that. And so a sodium atom has 11 electrons, a sodium 1 plus ion, 10 electrons. A nitrogen atom, 7 electrons, a nitrogen 3 minus ion, 10 electrons. Magnesium atom, 12 electrons, magnesium 2 plus ion, 10 electrons. Fluorine atom, 9 electrons, fluorine 1 minus, 10. And finally, oxygen. I should have given myself a little bit more room. But oxygen with its 8 electrons, and oxygen 2 minus with its 10 electrons. So all of these ions have the same number of electrons. But if we think about the number of protons they each have, sodium sorry, 11 protons, nitrogen 7 protons, magnesium 12 protons, fluorine 9 protons, and oxygen 8 protons. And so nitrogen only has 7 protons trying to hold in 10 electrons. So that's going to be much bigger because there's not as much pull holding in those electrons. Versus magnesium, 12 protons trying to hold in that same number of electrons. It's going to pull them in a little bit more. And so whenever you have what we call an isoelectronic series, an isoelectronic series is just a series of atoms or ions that have the same number of electrons. In an isoelectronic series, your size will decrease as your atomic number increases. And that should just make sense if you really kind of think about it. Just think about the structure of the atom. And so to sum up our periodic trends, as we move through the periodic table, atomic radius increases as we move down, and it decreases left to right. Ionization energy decreases as you move down and increases as you move left to right. Electron affinity as you move down becomes less exothermic, and as you move across, it becomes more exothermic. And remember that this is all tied into how the electrons are arranged around the nucleus. And so that's all for this little supplemental lecture on periodic trends. I hope you have enjoyed it, and I hope everybody's having a great day.